Formula 1 or F1, with 70 years of history, have 20 races per season, 10 racing teams including Ferrari, Red Bull, Mercedes and more.
So ladies and gentlemen, are you ready for Formula 1 in 2019?
Formula 1 is the top pinnacle of all motorsport racing events, where racing teams with marginal difference in performance fight toughly and closely for the championship. There are 300 sensors in the race car, generating 20 gigabytes of data that are sent to the factory to run simulations in real time and provide strategy insights to the race strategists at the pit wall. Our model aims to optimize the pit stop strategy, which is extremely crucial to the race result. Race cars go into the pit and change for a new set of tires. A pit stop takes around 2 seconds to change tires, but 20 seconds to travel slowly at the pit lane, which costs a lot of time in a race. So the question is, when to go in for a pit stop, and which set of tires to put on? Answering these two questions essentially give an optimized solution to the best pit stop strategy. As a proud Ferrari fan, a proud Tifosi, I would like to dedicate this project to Scuderia Ferrari F1 team. The model we built aims to improve Ferrari's pit stop strategy and gain better results. So let's begin. We would like to train a machine learning model for this task. It takes in race-related data for training so to predict the final position of a racer. The combined dataset has 17 input factors concerning position, pit stop and tire, weather and track, and one result label of final position gain. There are 1,134 records from the 2016 to 2020 seasons, which falls in the model assumption of dry weather and 1 to 2 stop pit stop strategy. The first generation of model is created by using TensorFlow Keras sequential model. Overfitting occurs by modeling the training data too well but lack the ability to generalize the knowledge. So we adopted several strategies to solve overfitting, such as simplifying the model, normalization, and regularizer, adding more data, etc. Luckily, the overfitting problem is solved, but the weird situation of testing data having a lower loss than training data is observed. It is due to the model predicting an average number of 0 instead of other position loss. But this time, even if we change the result label to final position, which has an even distribution, the prediction still insists on predicting average numbers to reduce the loss. Even so, predicting total race time and sorting the result is still inaccurate to conclude a prediction. However, the technique of sorting results of initial position minus predicted position change gives us a very accurate result. We ran 40 tests on races in 2019 and 2020 seasons. Even though COVID-19 forced F1 to make a whole new race schedule with 5 new tracks, yet the average error in predicted final position is contained at plus or minus 2.22 positions. For the safety car model, we are predicting the best pit stop decision during the safety car scenario. When there are hazards on the track, safety car leads the cars slowly to let the marshals clear off any blockage or debris. Quick decision is needed to notify the drivers either to go into the pit or stay out on the track. We adopted similar model structure as that of Model 1, but we included input features that concern the current position, tire, and pit stop decision at the moment the safety car is deployed. We evaluated that the second model's average error in predicted final position is contained at plus or minus 2.0 positions. We can conclude that the model predicts the final position accurately. Hope that this model helped Ferrari score higher in the next seasons. Forza Ferrari!